Okay, C495. I'm just recording the continuation of the last class. We started creating our math foundations. I'm just going back to show where we are, and let me show you that bottom for lower base, which create. We added the math foundation, which we start with 8 feet. Inches mat. I think material we use mat here 5000 psi, and then we chose mat type, right? There is a couple of type. I think typically the mat, like the relatively deep beam member, we use a mat type so that internally I think ETABS and SAFE include their shear deformations. All right, and additionally, after we define the section properties, and we also define the spring constant, those are representing the soil rupture, modulus of rupture, typically given by the geotech engineer or geotech engineering book. Typically provides some formula which we calculated and assign the spring constant vertical spring at this point, and laterally we didn't calculate anything yet, so this is mostly vertical components we are more concentrating. And since the building should not move around x and y dimension, I assign some translation constraint x and y. So as you can see, the 3D model has all gravity load that superimpose dead load and live load and the wind. So first thing I want you to just remind yourself about the spread footing design, which one thing what we did, typically if you have a dead plus live or service load, you calculate required total area of the footing, right? So to meet the soil bearing stress less than the allowable bearing capacity. So here at this point, I set it up all that and both dead load and live load. Especially high-rise building, we consider live load reductions. So I think here might be assign some live load reduction factor here. So this is a kind of approximate live load reductions. I think eventually, if you want to go very detailed, you should calculate for each column. But since this is in general and a multiple story, the code typically allow about 60% of reductions, which is live load reduction factor should be 0.4. For some uncertainty, I just typically use 50% or 60% of live load reduction for foundation design. All right, obviously there are many structural engineers their judgments, so don't just take this always the granted. So you need to use your engineering judgment. But 0.5 is good starting point. So what I'm gonna show you, first of all, load combination is the method, right? That plus live load, and also that plus 0.7 of live ran wind, which is service wind. So that is kind of cases. I'm gonna show you the soil bearing stress. So first thing, that plus live soil bearing. Uh, Before we do that, let's change the units. So looking at the soil bearing, we typically using kip foot because a larger scale kip and foot. So current soil bearing, we given 10-ton soil. So we type the control ranges minus 20 KSF to 0. So all negative number means this mat experiencing total compression. So what you can see, minus 13 KSF, right? that plus live load, you can see that most of loadings, significant loading is come from your concrete wall, which self-aid is predominant, and also the center concrete wall is supporting the floor, half of floating loads of the tower. So you can common sense that you can see that intensive gravity loads that plus live load is coming through the concrete wall. So we have habits that soil bearing occur at the middle center point, minus 13. So based upon our assumption, minus 20 and is way enough so that it meets our soil bearing capacity. And also let's check the interaction between that and the wind, so that the first case is the first case from the 12 cases of the wind, which is wind is blowing in X direction. Obviously, wind effect, rocking, tension, and compression on the right side, you experience most compression, summation of compression stress on the right side. If you move it 2, you can see that wind is blowing in Y direction. So the center of the highest soil bearing shifted to the top, right, on north, which means wind is blowing and bottom to top. All right, so I think you could kind of include that this is procedures, a soil bearing check, because of this our math performance, and just confirm should be less than our soil bearing capacity, right? All right, so next move, we'll just spot check the our shear stress. Let's see, what do we have? Okay, so here, this is an ultimate load combination, S1 to S6. S2 is 1.2 that, 1.6 live load. Okay, so this is a load combination, ultimate load combination. We have to check all the shear stress. Now shear, in terms of shear, you should aware of that what is a concrete shear. Capacity, right? So typically two-way the punching shear, and one way we checking around the mat, and typical formula of two-way punching shear is 5,000, okay, times, let's see, 0.75 times, 0.75 times, what's going on, 0.75 times 4 times square root. All right, so this is concrete two-way punching shear, the formula. So whatever just the shear stress exceeded this, we may have to consider either increasing concrete strength or thicken up the mat, or considering shear stress, shear reinforcement. So 212 psi. So in the shear check, this is we choose the shear stress check. S3 and 23 is our relevant shear stress. Okay, we need to change the unit as well. PSI. Okay, type the two-way concrete punching shear capacity. So you can see this. So most of the color contour between minus 120, 112 to positive 112, right? they're all okay, but we have some high significant shear stress at the corner of the wall, which is typical cases. And then let's check the S2, right? S2, you see there's some local stress concentration, and including the wind effect, you'll see another higher the shear stress at the corner, especially on the extraction wind blowing, right? It creates some significant shear stress, which makes sense, right? Because it's a wind and gravity effect is sum them up and cumulative and causing some high shear stress. Then you need to now look at this 3D model. We have all sign convention X and Y. So shear stress, you need to consider both X3 and 2-3 direction, S13 and 2-3 direction. So especially, let's go back to S2. You see now the shear stress contour is gradually changed in Y direction because of S2 is in parallel to the Y direction. So you could see that the contour gradual gradients, I think, give us the general idea of a load path. This is shear stress direction, right? All right, so I think for now, this is just kind of checking procedures. We might need to increase the mat thickness a little bit at the only bottom under the wall, or we assume that this much of the shear stress exceedance, we may consider shear reinforcement. We'll talk about it more detail later if we have a chance. But I think this class is overall. I just try to give you the overall checking procedure. It's pretty much similar to the year fling design. Nothing different. Just this is a little larger scale, and you need to include all this the previous learning concrete design philosophies into the 3D. All right, so now let's stay here. Okay, so engineer, when you think that the mat thickness is reasonable at this point, or right, you may have to study and iterate to finalize the thickness. Could be two different thickness or just one constant thickness, but this is part of optimization procedure. And so once you determine that final thickness, you may have to start draw the design strip for flexural bar design. So for now, here I'm going to just assume more coarse the design strip. Choose the 50-50, so it's a 100 inches wide design strip. I'm gonna use it. You may have to use a different strip. It's totally up to you, but this is just example. Don't look at this as why. I think you should bring your all equivalent flame method idea, that column strip and middle strip, or you can bring your design strip width based upon your column spacing. But here, let's see, in A direction, I'm gonna for now draw one. And since this is 100 inches wide, I'm gonna replicate and in y direction 100 inches, maybe 15 covered. Okay, so this design strip, oh, okay, 100 inches design strip, I copy over, so I cover all entire mat. And also B direction, I'm gonna draw and then do the same thing. Okay. Okay, so all my design strip cover entire my matic, right? So I'm gonna use this giant strip for now. So the one thing that I'm gonna show you is that since I define design strip, the ETABS collect the design forces, resultant forces based upon this design strip width, and from their location, it will collect the bending moment and shear, and eventually we want to use those design forces for flexural design. So let's see here. There. So now let's check this on the plan, and we'll check the design strip forces. So this is the one example 1.2 dead, 1.6 live root, and we'll check the moment diagram. Okay, so yeah, actually you could see in general sense of the bending moment diagram for the mats on continuous spring. So you see series of compression and tension. This totally depends on the mat, the continuity over the soil, right? The area spring, and they're bending the kind of deformation shape. But you could see that all the design strip collect the moments along their entire length in X direction and Y direction as well. So this is something is typical the slab design as well, nothing much different. So I want you to just think about it, slab design. So let me show you the also shear force diagram in X direction and Y direction. So this is just design the strip forces we're gonna use for flexural design. So let's go to design now, move on. I'm gonna just go through, I want you to just go through this. At this point, I'm gonna choose the default. If you want to interest, just look through it. Maybe the minimum cover, something like that. Typically, this scale of med, I'm using number 11 bar. Oh, now I have to change the unit again. So I'm using inches, design, concrete slab, and preference again. The minimum cover. Since we are pouring the concrete over entirely dialectically soil, we need clear cover, but also we may end up with a couple of layer of bars, right? It could be 2 layer or 1 layer, 3 layer, depends on. So I just assume maybe something like the 5, and top clear cover I just approximately use 3, and using this concrete cover, I'm gonna also I'm ready to design. So this is a load design load combination, right? Just one thing that I'm gonna make sure, and this is all the ETAP things. You need to go through all this. But that I think previously somebody actually mentioned about the wind loads. If you want to using ultimate wind loads, yeah, ultimate wind loads. So you go through all, but you need to either using load factor for your service stability deflection check, or you maybe create another load, wind load, which is service load, and using service wind load, wind speed, you can use that load cases. But one thing I want to point out, since my ETABS has a good tool, they are automatically setting up this load design load combination with a given properly established load pattern that's automatically set it up load combination. This is actually quite some efficient and time saving, but it's always if you have on another load cases, it's gonna generate another type of right load combination with the service wind loads. So again, I need, and it's a totally engineer judgment. It's you need to set it up your design and work load path, but should be consistent. You should be always aware of it, how to use the ETABS. All right. So concrete slab, we'll go back to concrete slab. The thing is, I'm gonna check the selected story for slab design, right? And this is a pretty new feature. New ETABS Ultimate version include a save feature, which is great. And I'm not gonna just run the displays. This is for design exercise, so I'm gonna start run the design for the mat flexural reinforcement, and go to design again. And I'm gonna, after the design is complete, you could go and click the display flexural design. There are two methods, finite element based and stream method, but I prefer stream method. It's more intuitive so that you could choose the number of bar and size and spacing. First of all, we're going to show you bottom bar. Typically, we're using typical bar for all the design and the selection of the rebar size and spacing. All right, there are many ways to do this. Some engineer using the required area of steel, or I think Save ETABS has this feature. I can visually kind of choose the reasonable bar size and spacing and number of bar and location. So there is no absolute way to do this, but this is actually my practice. Typically, if you're interested, just go through an exercise. So here is kind of example. So first of all, we need to include the minimum reinforcement. I'm just looking in the bottom bar in X direction only first. So if everything is, I assume, correct, most likely, when I choose number 11, 12 inch on center, basic bottom mat, and additional bar, I choose number 11. Those are all the bar shown on the screen is additional bar. So okay, we still need a lot of additional bars. So maybe either you could consider as, for example, 6 is a bundle, or maybe that's too much over, maybe 8, something like that. So because the number of bar is not going to be always clean, so you see that some more amount of rebars we needed under the concrete wall, which is a lot of, you know, the forces coming from the wall eventually that require a lot of rebars. All right, so bending, okay, rebar is because of the bending moment underneath. So but you could see this, you could double check all the bending moment under the wall, right? And then that actually causing the amount of bending moment, and then the required amount of bottom bar. So you need to do some iterative exercise. So if you think this is a reasonable bar and additional bar, you can kind of sum them up, redistribute it along the the width of the wall. You could do that, but also maybe you can play around the bar size and spacing and find out reasonable bar size and spacing. The number of bar and spacing, and also different number of layer, right? It's all engineering judgment. It's just how this or the number of bar will fit, and within in the right place, and but also should be constructible. So here, number 11 and 6 means it's not always 6 inches. Some people may say that, oh, it is too closely spaced. Okay, this is engineering all the exercise. It doesn't have to be number 11 6 inches. I do not prefer to use a 6 inches spacing. If you consider some splice, it's going to be very compact, condensed, the dense rebar layout. Instead, you can consider is the bundle of number 11, right? Two number 11 at 12 inches center is equivalent to number 11 at 6 inches center, right? So there are many ways to do this, but this is something you could consider. First of all, understand based upon design forces, SAFE and ETABS give you the required area of bars. Is the size of bar and spacing is all engineering judgment, and based upon constructabilities, you can choose that what kind of bar and spacing and number of layer you're gonna use. This is all engineering judgment. All right, let's take a look at it in Y direction. Is pretty much the same. I turn up the A direction. It's pretty much the same, right? Under the wall, you see the more reinforcement is needed, which is so that I can add it here. Top bar, bottom bar. Okay. Yep. Okay, bottom bar, and I'll change to top bar. Right, top bar showing different magnitude and slightly different location. Obviously, the bottom bar typically we need more because of you see the bending of the deformation shape of the mat. You'll see what is the bending shape. Obviously, we need to provide the bars under the tension side, right? So, all right. So I think this is in general the floor framing, not floor framing, mat foundation flexural bar design procedures. This is the only one we have it. If you can use a different method using some forces, you play with the spreadsheet, you can do that too, but this is visually more intuitive. You can kind of iterate and see and find out, and you can sum them up, and if you can place the rebar at the right location, I think that is in general practice. Okay, so I didn't show the punching shear check. Maybe we can run the punching shear check whether there's something punching related issue. Maybe because we have an obligate column, so we may have to double check whether this is the punching shear is really critical. Then we may have to consider to increase the mat thickness, or we could add some additional shear reinforcement, or we can do something for this punching shear. Okay, or maybe we can extend this mat a little bit, or increase the mat thickness a little bit, concrete strength, and or we can add some relatively big column underneath so that we can get the more in B sub 0 critical zone length. All right, I think I'm gonna stop here. I want you to just watch it and take a look at it, and we're gonna discuss a little more during class. Okay, bye.